Edx M3 June 2011 question 6. This one's on vertical circular motion, and it's one of the old favourites on motion in a vertical circle of a particle attached to a string. So as usual, you need to take some time to read the question and just pause the video and then carry on when you're ready. Okay, here's the first part of the question. I've already created the diagram. On my diagram, I'm showing a general position with an angle theta. They don't tell us to use that angle. I'm showing the initial velocity and a general velocity at a point V, because I'm anticipating creating equations for V squared using energy, conservation of energy. Now this first part of the question just says show that P will pass through B. So think about that carefully. Show that P will pass through B. Now, it isn't going to be enough to just show by conservation of energy that it's got velocity at a height of A. Now think about that for a minute. You might like to pause and think what's missing. I'm going to start by doing that. Okay, so we'll start by looking at the energy equation from the point A to B. Let's do that here. Energy going A to B. Right. There's the total KE plus GPE is constant in this sort of problem because there's no work done by the tension in the string. So the KE, half mv squared, becomes a half m 3 root ag. Square that to get 9 ag. If we take the 0 for potential energy as the level of A, that's the first sum then of kinetic and potential energy. It's just kinetic, and that's equal to half mvb squared plus mg times the height, which is A. And that gives us, fairly easily, that works out to be vb squared. The velocity at b squared is 7ga. Now, what's missing? Well, we don't know if it performs a complete circle, if it actually gets right to the top with tension still in the string. So what we've got to do is just show that with that vb, that would be enough to keep it going in circular motion with T tension in the string greater than 0. So at the top, at B, the equation of motion down towards the center then, if it's at the very top, it will be T plus mg equals m vb squared over A. So T plus mg will be 7mg. Now that means, obviously, that T equals 6mg at the top, at B. So that does now prove that it goes through B. So T is greater than 0. T greater than 0. Therefore passes through B. That's what I'm trying to write in the corner. I think the corner of my graphics tablet is a little bit dodgy down here. I'm trying to write passes through. I don't know what's wrong with it. Passes through B. Apologies for that. Okay, that's part A done. 6 marks. And the catch there was that students might have just stopped at getting VB squared equals 7GA. You have to show that the tension is greater than 0. Okay, find the speed as it reaches C. I haven't got any room on here to do that. Let's go to the next slide. Right, this shows part C, but let's just do part B as well. The speed at C. Okay, for the speed at C then, we can just use energy again. Half mv squared just check this energy equation. Half m 9ag for the original kinetic energy, plus mga, that's the original potential energy then at A compared to C, and that's equal to the kinetic energy at C, half m vc squared. And again, a simple bit of reordering there and tidying up gives you vc squared equals 11ga. So vc is root of 11ga. Right, that's the second part done. That's part B. Part C, on the top of the screen, and I've drawn a diagram for this. Part C says, as P passes through C, so at the bottom here, it receives an impulse, it's hit. And immediately after this, the speed is 5/12, so it's been reduced quite dramatically. So all of a sudden, the speed at C is now much less, so it's no longer going to go in a complete circle. In fact, it's only going to go up a little way and come to rest. So I've drawn a diagram showing the point at which it comes to rest, and I've shown the radius at an angle alpha. Importantly, what we need is the height difference. I'll do that in green here. H equals the height difference here is A minus A cos alpha. We're going to need that. Now, let's do for part C of the question then, let's do energy one more time. Energy from the bottom to when it comes to rest. So half m v squared, 25/144 times 11ag. That's the initial kinetic energy, and as it comes up and eventually comes to instantaneous rest, all that kinetic energy goes to gravitational potential, and that's your mgh, using the h that I've got in green just above it. Right, well the mga cancels out, and we get 1 minus cos alpha equals 25 times 11 over 144 times 2. So cos alpha, nearly that, 13 over 288, I got it, giving alpha equals 87.4 degrees. Just check part C, find the angle between the string and the downward vertical. That's what they want. Good. So, bit squashed in there, I hope that's okay. Let's just check the marks for the parts A, B and C then. Just going back to the first part, here we are. For the first part then of the question here, we've got, let's just see, for 6 marks, we've got an M1A1 for the energy equation that gets us 7GA. So an M1A1 for that. Okay. And then we've got another 4 marks, which is 2 more pairs of M1A1 for the finding the expression for the tension at the top here. This is M1A1. Again, my pen is being a bit hesitant to write, M1A1, and here, M1A1. So that was your 6 marks, basically 3 pairs of M1A1. And for the second bit, part B, finding the velocity at C, where are we for that? That was just 2 marks for that, so an M1A1 for that, for the 11GA for this bit, for using energy and finding the correct B, and 4 marks for the last bit. And you guessed it, it's a couple of pairs again of method and accuracy. So using the energy equation and correctly sorting it out to find the angle. Okay, so that was 4 marks for part C. Right, that's question 6 from June 11 at Edx M3. Thank you for listening.